Good afternoon, everyone, and thank you for joining us for this exciting live talk. Today we'll be learning all about the dark universe and the amazing scientists who are exploring it using the Euclid Space Telescope. Telling us all about this is Benjamin, who works as a Professor of Astronomy at University College London. Over to you, Benjamin, and thank you for helping us explore space.
The big sticker on with the Euclid sticker, and that's inside that bit is where we have the Euclid Space Telescope. So by now it's out there where it's supposed to be. I'll show you a bit more of that later. And you will also find a link in the chat that maybe your teachers can show you later, where we have a video that shows the launch. And of course, that was very, very exciting and nail-biting for us. The Euclid team is more than 2,000 scientists all across the world working together, and some of us have worked on this for way more than a decade, so it's been a long time coming. Of course, it's super exciting to finally see it go off into space. Now, just to give you an idea of the size of this, so you see the top there with the sticker on, and here is a picture, putting it to scale. The shell that it was in, it's got the fairing, comes back down to Earth, so it can be reused, and you see it there on a big lorry. And so that gives you an idea of how large this actually is. You can also see the brown smudges here at the bottom. That's where our sticker used to be. So we, meaning the European Space Agency, we were very keen to have a big sticker of Euclid on, this one here. The company who launched the rocket was not so keen, and now we know why, because it burns up, it gets very, very hot, and so you now have a big dirty smudge here that someone needs to clean up. Fortunately, not me. Right, so if we now take a look at what's inside, this is a model of Euclid, and so you get an idea of what it looks like. So it's been wrapped up safely inside. What you see here, of course, is some big solar panels. You recognize this. This is how Euclid gets its power. So this will always point towards the sun. And in this barrel here, you have a telescope. So let me describe a bit more of what's in where exactly. So here is a still picture of the same thing. So here we've got the telescope again, and here at the bottom you have a big mirror that collects all the light, as a telescope should do. You see here the mirror before it went in there, and the size is about, if you take your arms and stretch them out sideways, and then from the fingertips on one hand to the other, that's about the size of the mirror. So this is about as big as it is. It's just over a meter across. And then we have a second mirror. You can just about see it here. It's much smaller. And that takes the light that the first mirror sends up and focuses, it bundles it down and sends it back through the hole in the main mirror here into this box down there. And in that box, we have cameras that take pictures using that light. So that's the basic idea of Euclid. As we said already, solar panels, very important. We need to have power, we need to have electricity on board. And so this bit will always point towards the sun. And at the same time, it's also a shield, because the sun is very, very bright, even out in space. And this telescope is very, very sensitive. And so even a tiny bit of sunlight can completely damage and overwhelm our cameras. So we have to be very careful with this. And of course, we need to be able to talk to Euclid. We need to tell it, please take a picture, please look in this direction. And then we need the pictures back on Earth. And for that, you see here this antenna. It receives the commands from the ground control that tells Euclid what to do, and then it sends pictures back to us. These are the key components of Euclid. Right, so before we send it off, we could take a few pictures. And so what you see here is a big mess. These are actually the cameras. You see one big camera here, so they're a bit bigger than the ones that you might find in a smartphone. And the second camera is over here. You just about see here in blue, that is the window where the light will eventually go in. Okay, again, for size, you see a person standing next to it. And here again, admiring the telescope as it's being assembled. Now you see they're all wearing protective clothing and even a hairnet, because this is in a clean room, because we don't want any dust or a single hair to end up, for instance, on this window. This would completely mess up our pictures. We have to be very, very precise. Even if you've got any little smudges on our mirror, that would already affect the quality of the images that we take. So this has been done very, very carefully. And you also see here on the real Euclid, it looks very nice and golden, very shiny. So this is actually not real gold, but this is essentially a foil that helps shield Euclid from any hot sunlight that might come upon it. It's very similar to rescue blankets that you find in the first aid kit, which also shimmers golden. So it's not real gold, it's just a kind of plastic. Right, so now to understand what Euclid is all about, maybe a good starting point is to look into who actually is Euclid. Why was Euclid named after this guy? So here we have a picture of him. Actually, I said maybe because no one really knows what he looked like. He lived way more than 2,000 years ago. We don't even know when exactly or where he was from. But what we do know is that he wrote books and worked out for the first time how geometry works. So geometry is the science of shapes and distances and how you measure them. And he was very good at that. And we still to this day use his mathematics to do that. So you learn aspects of this in school as well. I might have done so already. In particular, on Earth here, we care about how to do straight lines. And Euclid had very important sort of theory on that. And so one way to do this is if you take a torch and you make a light ray, then that is very much a straight line. We can actually use that to define a straight line between 2 points, and then we of course can use a ruler, for instance, to measure a distance. Now, there's another chap here on this slide on the right. I'm sure you've seen a picture of him before. He lived much more recently, about 100 years ago, and his name is Albert Einstein. He was a famous physicist of the 20th century, and amongst the many great things that he did, he worked out how gravity works. Gravity is the force between massive bodies that attract each other. So for instance, you have a certain mass and the Earth has a certain mass and you attract each other. And that's the reason why you are not floating off into space, but rather probably sitting on the floor or on your chairs. And so Einstein was the chap who really worked out how this works. And he came up with a surprising new thing that no one had really anticipated before. Namely, he said that, well, it's not only masses that attract each other, heavy things, but also light. So for instance, if I've got light that comes from a star up here, and it passes by a big heavy thing, this is a picture of our sun, for instance, then the light actually gets bent by this. So it doesn't run in a straight line anymore. It actually follows a curved path. It gets attracted by that massive body. And we know now that this really happens in the universe. And this bending of light is actually what Euclid is going to use to understand more about the geometry of the universe at large. I'm going to look a bit more into that now. Right, so here you see this again. We have a big mass in the universe and we have got very, very big things. The biggest things actually that we know in the universe, much, much bigger than our own sun, huge systems, and they are very good at deflecting light, letting it go in a curved way. And then if you've got light from a distant source sent out, you've got something heavy in the middle, it actually starts to bend it back towards our telescope there on the right. Okay, let's look at that one more time. So you see what happens. It focuses the light. It acts like a lens. We actually call it a gravitational lens because it's gravity that does it, but it works otherwise just like a collecting lens, like you might have in your glasses or in a little telescope. Okay, and so if we look at another picture there, so here we again have a distant light source, sends out light rays, and now we put a mass in the middle. It starts to bend the light towards Earth here, the little ball on the right. And if we see now how that looks on the sky, we see the big mass. That's the bright thing in the middle. But then we see multiple pictures of that object in the background. And that is indeed something we can see in the real universe as well. So this light bending causes these kinds of special effects. And then we can use telescopes like Euclid to actually observe this. Now, what is this all good for? Right, before we do that, I need to explain to you exactly what a galaxy is. a galaxy plays a key role in this whole business. Euclid will actually observe several billion galaxies altogether. Okay, so here we've got a particularly pretty one, the real image. And what you see is a sort of swirly pattern here. And this is indeed because something swirls around. So we have lots and lots of stars that swirl around this bright center here. And each and every galaxy has, again, lots and lots of stars in it. Again, several billion, usually for a galaxy. You happen to live in a galaxy as well. Our galaxy is called the Milky Way. You don't see that swirly pattern because you're actually right in it. So if this was the Milky Way, we would be living out here in the quiet outskirts, not far from one of these bright spiral arms here, and we would be one of these very, very faint dots. That would be the sun and the solar system. And you see this haze here. It looks a bit fuzzy. These are actually, if you look closer, these are all individual stars that all send their light out and together make this pattern. In the center of the galaxy, you actually have a very massive, a very big black hole. We're pretty convinced of that now, that eats up more mass, but it only affects here the center. Out here, we're fairly safe, fortunately, and it's these many stars that make up the light of the galaxy. Okay, so whenever I say galaxy, and I show you plenty of pictures going forward, you always look out for swirly patterns and this slight fuzziness that comes from many, many, many stars sitting together. This galaxy is fairly close by, and when an astronomer says fairly close by, you have to take that with a pinch of salt. For instance, the nearest galaxy to us, our sister galaxy, is called Andromeda, and that is really, really very close by my standards. But still, even light takes several 100 million years to travel from that galaxy to us, and light is the fastest thing we've got. So the distances are absolutely astonishing. Now, again, this galaxy is nearby. We'll see galaxies and other pictures that are much, much smaller and hence much further away from us. But these are the galaxies that Euclid is particularly interested in. There's something else that's very interesting about the galaxies. I told you they're swirling around. Now, we can't see this because they're so far away that although they're actually moving fairly fast, we just see snapshots. It would take hundreds of millions of years to actually see the whole thing move. But we can do this with a model, with a computer simulation, and then you see things like this. Okay, so here we've got a galaxy. We're looking upon it. You see the spiral swirly pattern, and you actually can now, because we sped up time, see that it's swirling, that it's rotating. But I'll do it again. They do it in a different way. So have a close look and see if you can spot the difference between what is happening on the left and what is happening on the right. I'll give you a moment. Maybe you can see something there. Let's do it one more time. Right, so in the center, in the middle, it looks fairly similar what these two galaxies are doing. But look here in the outskirts. You see here things move very slowly. Let's do it one more time. Whereas here, things are moving relatively fast. Okay, so further out there, these galaxies behave differently. Now, the trick is the galaxy on the left-hand side is what we would expect. If we just count the stars that we can see on the left, they all interact via gravity, they attract each other, and we have the swirly effect in there. And then we would expect the outer bits to go more slowly around. So the left-hand side is very much what we expect, but that's not what we observe in the universe. We have tricks that we can actually see how fast stars are moving. And if we look at that, we actually observe what we saw on the right, that the outskirts are moving fairly quickly around the center of the galaxy. And all galaxies do this. Now, if you move fast, you've all done this if you've been on a fairground, right? If it turns quickly, you feel a force that pushes you out, right? Like you're about to fly away. The same thing happens to stars. So they should actually, if they're moving that fast, they should just fly out. Gravity should not be strong enough to hold them back. But that's not what's happening. So there must be some extra mass, something extra heavy inside that galaxy that holds it in. But we can't see it. We only see the stars that are there. So it's heavy, it has gravity, and it's dark. And this stuff we call dark matter. When astronomers call something dark, it simply means they can't see it. So there must be something extra there that holds in the stars on the outside. And it's not just in a given galaxy, it's everywhere in the universe. All galaxies do this, including our own Milky Way. So there must be dark matter here in our Milky Way as well. We don't know what it is, but of course, we are very keen to find out more about it. Now, before we do that, let's do a little test so to check that we really understand galaxies well. So I'll show you here this picture. This is a real picture. It was done with the Hubble Space Telescope. It's another space telescope out there. It's been there for a long time. And it depends, again, on how big the screen is that you're looking on. But have a good look and see if you can spot some galaxies. Again, this picture was taken in what looked like an empty part of sky. But if you take pictures long enough, you actually start to see things everywhere. So just maybe point towards it on the screen. When you think you spotted the galaxies, just point there. And I'll give you a moment to do so. And then I'll point out a few. Okay, well, the good news is you could pretty much point anywhere you liked because all of the specks that you see, pretty much all of them, will be galaxies. So there's some more obvious ones, namely, I told you, look out for swirly patterns. Here is one. Then here is a nice swirly pattern as well, right? Look out for fuzzy things. That one, definitely pretty galaxy. Here we've got both, some swirly patterns and some fuzziness. But even the faint specks that you see everywhere, almost all of them will be faraway galaxies. They just look like spots because they're so far away from us. There will be the odd star here, and the stars belong to our own Milky Way, so they are quite close to us. But only a few. Most of these spots here are all galaxies. So if we have a very good camera and a big telescope and are out in space, so we don't have the atmosphere that's in the way, then we take deep pictures and we can see lots and lots of galaxies. And of course, that's exactly what Euclid does. Right, so I told you, galaxies also give us a hint that there must be something called dark matter. Now, it goes beyond that. If we now have a computer model and we put in lots and lots of matter and just switch on gravity and let this run over time, the following happens. Have a good look. So here we put it into a big cube and we just switched on gravity and then see what happened. So this box here is a simulation, is a model of our whole universe. Now run it again. So we start from some early time in the universe where the box looked, oh, that was a bit quick, where the box looked fairly smooth. And then you see what happens. It starts to clump together and it starts to make a sort of web-like structure. It looks like a very complicated spider web that you can see at this time of year out in the morning. And this is what we call the cosmic web. So we think actually that dark matter is not only hiding in galaxies, it is everywhere in the whole universe. And actually we cannot explain how the universe looks like without putting quite a bit of dark matter in there. So we really rely on it, although we've never seen it. So how can we prove that there is dark matter in there and how much is in there and how it actually clumps together if we can't see it? And that's exactly what Euclid is going to do, and that's where the light bending effect comes in, because that will help us. Right, so just to illustrate that again, on the left-hand side, this is what we would see as a cosmic web of dark matter. Looks rather pretty here. Of course, the color we don't know. On the previous slide, we just painted it blue. Here we painted it pink. We have no idea. It doesn't have any color, probably. Okay. And then on the right-hand side, since we can't see dark matter, this is actually what we would see, because these are the galaxies, like the picture that we saw before, dotted all over, but they're not random. They do follow the dark matter. They sit like the dewdrops on a spider web, right? See, where there's lots of dark matter, you also find lots of galaxies. Or here, for instance, along a filament, one of these spider web strings. And here we see a string of galaxies as well. So this is what we observe. Now, how can we actually detect the dark matter? Well, so one way, of course, is we just pick some up. I said there should be some in our Milky Way as well. Actually, we think that right now there's dark matter flying through your body, and probably quite a bit of it. The problem is dark matter, it doesn't interact with the normal matter that you are made out of very much at all. And that's why it just flies through you and you don't even notice. It actually flies all the way through Earth and not much happens. But we hope that every now and then, one of these dark matter particles will bump into a normal piece of matter, and then we can detect it. We can see the bump that happened. And so my colleagues, who are particle physicists, try to do this. They go into a deep, 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 dark underground mine. This one here is in America. And they build a huge tank. They go so deep underground because they don't want any other effects happening, just that. And then they wait. They wait for a long time in the hope that at some point in this huge tank, one dark matter particle will bump into the matter, and then their detectors will say, "Up, I saw it." Alas, so far, that has not happened yet. We have not detected a dark matter particle, although we've been looking very hard. It's a bit mysterious, but my colleagues keep trying, and maybe one day you will certainly find it on the news, they detect it. So while that's not happened yet, astronomy, so looking out into the universe, is the only way to find out more about dark matter. Right, so I told you we can use the light bending effect to work out why. And I give you an idea here. So this is again a sketch. This is not a real picture of some galaxies, okay, similar to the pictures I've shown you before. And now what's happened here is that I move a lens, a big mass, in front of it. Okay, and the effects that you see distortions, the objects move about, sometimes they even seem to form a ring. These are due to the light bending effect. And now, if I ask you, where actually is that lens at this point in time? Or can you maybe point with your finger where you think the lens sits at any given moment? I'm sure you won't struggle to follow it. Right? You can probably tell it's moving just from the left to the right through the image, but you can't see it. And yet you know exactly where it is. And you probably also have an idea of how big it is. This is the great thing about this gravitational lensing effect. We can even see dark matter that doesn't send out any light, just due to its gravitational bending effect. And that is exactly what Euclid is going to do. So we're going to look at all these distant galaxies in the sky, and we're going to look at these patterns that you see here, these distortions and ring shapes. And from that, we can then build a map of the distribution of matter in the universe. And you remember the cosmic web, that is exactly what we're trying to see. And then we can measure it and understand its properties, just like old Euclid used to do as well on Earth with lines. So just to prove to you that this is not just a cartoon, right? Look again about these sort of rings that form in this cartoon. This is a real image. So what you see here in the center, that's our lens. That's a heavy galaxy, probably lots and lots of dark matter inside it. And as it happens here, there is a galaxy right behind it. It's very far away, and it's probably a nice swirly blue galaxy. And you see it gets distorted into almost a perfect ring. That's a very special pattern. No galaxy just looks like a ring by itself. So we know, aha, gravitational lensing has for sure happened here. And we can use the size of this ring to essentially weigh that big galaxy and tell how heavy it is. This is how this whole thing works. Now let's come back to Euclid. So where are we with this? Here we've got another picture another nice one. And again, if you look carefully, you see here these are arcs all the way even further out here. No normal galaxy looks like this. They've all been stretched into this pattern by the big galaxy here in the center. And that, of course, we can use, right? Even these small smudges, that those galaxies, they will all have been a little bit distorted. And it works just like a normal glass lens here. It's the shape of a ball, and you see the same thing happens. You see these arcs, and you see it sort of stretched out. So the same idea. Right, now, where are we with this, and how can we see them? For me, it's very loud. I'm not sure if you can hear this. Okay, so we just started out at a normal night sky, which you might see in a dark space. And the idea is what Euclid can do, it collects light really, really well. And you see now fainter things popping up that you cannot see with the naked eye. And if you go further and further, you see even more things. Just keep looking. Right? If you collect more and more light, more things will show up. And eventually, you get to these fantastic pictures of which I've already shown you a few. There we go. And in this one again, you can spot some lensing effects. Right? You see these streaks and stripes from the gravitational lensing. So we can then look at the sky and look very deep and carefully, and then the sky becomes rather big, and so it's going to take us all of 6 years to actually map the whole sky with this and understand where the dark matter sits and how it is distributed. Right, so where are we? Euclid was launched from this little ball here. You all know it very well. That's Earth. And it was sent on a mission far out. This is a spot that we call L2. It's quite far away. You see here the moon. Most satellites actually swirl around Earth about here. So we send Euclid much further away. And the reason is that we don't want it to be disturbed by anything that's near the Earth or the moon. We want it in a nice, quiet, dark spot. And we make sure it's further out from the sun because, again, the sun is terribly bright for Euclid and we need to shield it. Right? The only thing we want to collect is some nice power, electricity from the solar panels. So this is where it goes, and it's already arrived there, and it's doing little loops around this point, and then starting to observe and scan the sky. Now, if you don't believe me, well, my colleagues were a bit skeptical as well, and they were observing with a big telescope on the ground, a 4-meter telescope on Hawaii. 4-meter telescope, it probably just about fits into your classroom. Not sure what it looks like, but maybe only just. So it's a really big thing. And they looked at the spot where Euclid is supposed to be, and then they made a little video out of it. So what you see here are actually stars close to us. So these are nearby things. They flicker a little bit because sometimes you have a bit more cloud in the way, sometimes less, so it gets a bit darker and brighter. But can you spot Euclid on its way? Have a good look. I'm sure you can. There's a white streak zooming in from the right. Where are we coming in? There it is. And then zooming through. It's a streak because Euclid moves so fast that if you take a picture, it actually moves while the light is being collected. And then if you take a video, you see how it moves through. So that was Euclid on its way out to this distant, faraway spot. And you can't see it with the naked eye. You can do that only with nearby satellites, but with a big telescope, you can still see Euclid out where it's supposed to do its job. Right, and this is my last image for you. This is a special one. This is the very first image that Euclid has sent to Earth and that the Space Agency has now made public to us. So I'm allowed to show you this picture. So this just come out a few weeks ago, so it's very hot off the press. Now that looks a bit different to the other pictures I've shown you, and this is because we haven't carefully cleaned and analyzed those pictures yet. Astronomers always take pictures in black and white. The color images that you see are assembled afterwards, once we observed an object in different filters like blue, green, and red, and then we put that together by hand. So this is just one of them. And what you also see is these beautiful patterns here with six-fold symmetry, right? You see these. These are all nearby stars. They're fairly bright, And these streaks are simply picturing where our second mirror is actually held on by the telescope. There are 3 of them, and so that turns into this 6-fold symmetry. So it's got nothing to do with the stars themselves. This is the way the telescope looks like. So again, lots of these dots here are normal stars. And again, you know now, we don't care for the stars. We want to look deep into the universe. We want to find galaxies. Another thing you see is long streaks and then shorter ones all over the place, lots of them. You may wonder what that is. Now, this is actually nothing on the sky. This is our rather violent sun. The sun sends out lots of particles into a big wind out into every direction. When those hit the Earth, you get the beautiful polar lights. And at the moment, the sun is very active. It's in a rather bad mood. So we get lots of pretty polar lights. But a few minutes later, Euclid is hit by those as well. So it's bombarded by these particles, and they hit our camera and dump lots of energy, and that then looks like these streaks here. So this has got nothing to do with the universe. This is our own sun messing with poor Euclid. Hopefully it will quieten down a bit as we go on. But now you're experts. By now you know how to find galaxies. So have a good look and see if you actually can spot a galaxy in this messy image, despite all those streaks and the stars in the foreground. Have a quick look, see if you can spot anything. I'll give you a hint sooner or later. So there's one easy one, I think. Here is a nice big galaxy. You see the fuzziness, that's there. There's another big one which is nicely hidden. Maybe you spotted it. It's close to this bright star. There, can you see that one? There is another one. But then if you've got a good projector and you're eagle-eyed, you may spot many more. Here, for instance, another fuzzy one. We've got a galaxy there. Up here, there's one. This probably is one too, although we see it nearly edge on. It looks like a disc, like a sort of cigar shaped. That probably is a galaxy, and so on. You might have seen more. So there you get a glimpse of what Euclid is going to see when it's going. Right, so I'll stop with that, and I hope you have lots and lots of exciting questions for me. Thank you.
Thank you so much, Benjamin. That was so interesting and so much information that we can go away and maybe do some reading or learn some more, do some research. I know I'll definitely be going to have a closer look at those pictures because they're absolutely amazing. You could look at that for hours. So before we get to the questions, we did have some schools give us a shout out in the chat. So I'm just going to very quickly say good afternoon to Stonesfield School and Galley Hill Primary. We've got St. Joseph's in Halifax. We've got a school that's in Lancaster, another one in Grimsby. So we've got schools everywhere. And it's so great to see so many schools joining us. And the chat has been absolutely busy. We've got 93 different messages in the chat, some questions that would take hours to answer, but some really interesting ones. So I'm going to pick some of them, but I will be sending them all to Benjamin afterwards, and he'll be able to look at those questions and do some further research. And you never know, maybe your question might inspire some different research in the future. So a really nice question we had from the beginning was about maths and why is maths important when you're studying space? So I think beyond geometry, maybe what other kind of maths might you use?
That's a very good question indeed. Yes. So I can answer that in very general terms, right? As astronomers, we are doing physics. And if you do physics, you use mathematics as your language. This is how we try to express in a very precise way how we do things. So if I talked about Einstein, he was a very, very clever person and he worked out how gravity works. And the math that he uses, for instance, is quite complicated. It's not something that you learn at school. It's even something that I didn't learn at school and later on at university. And actually, it turns out that even Einstein didn't know the maths that he needed to know. So he actually, before he could do this, he had to go find some textbooks, learn about the maths that he didn't know, and then he could actually work out how the theory of gravity was supposed to be. So that gives you an idea in that there's a strong interplay. We use the mathematics to express our theories, how the universe, how nature works, and then the maths can tell us some answers, and then we can check that with experiments or as an astronomer with observations. So all kinds of maths, and you never know what you're going to need. It varies a lot. Everything that you learn at school, literally all of it, I use on a daily basis in various ways. So yes, maths absolutely essential to our work. But of course, it also is much more fun rather than doing it in an abstract way, right? We do it for a purpose. We do it to understand dark matter. We do it to understand particle physics, all these things.
Amazing. It's great to hear that all of our hard work at school doing maths is very important. So that's really good to know. We have lots of questions about galaxies and specifically, I guess, because it's ours, the Milky Way. So we had one question, why is it called Milky? And then another question about, is it the biggest one or are there bigger ones out in space?
Yes, oh, these are great questions. So I have an idea. Hang on, I just have to get rid of my leftover lunch because now I've got a nice model here of a galaxy. Right?
Amazing.
They look a bit like disks, and so now imagine that you're actually living inside one of these, as we do in our Milky Way, right? So you're sitting somewhere inside, and you're trying to look out of it. So what you're going to see, you can look out of it quite well in this direction and in that direction. But if you're looking this way, you see a lot of the galaxies. And we saw what that is, lots and lots of stars. And remember, I showed you the picture of the big galaxy and it looked a bit fuzzy. I called it fuzzy. You can also call it milky, right? It looks a bit hazy. And so that what you get is, if you look out in the night sky, you get a band where you see quite some sort of fuzzy, milky haze around you. And even the old Greeks, for instance, observed that. Well, they had much less streetlights, obviously, so that it was much easier for them. And that's why they call it the Milky Way. It looked milky, and it was a long band going across the sky. If you're in a very dark place, if you're lucky enough, for instance, to live in Scotland, in the Highlands, for instance, then you might get lucky on a clear night to actually see this milky band. And that's why it's called the Milky Way. Now, is it big? I need to answer.
Yes, is it big? That was our next question.
Yes. So our Milky Way is a fairly standard, what we call spiral galaxy. So similar to the one that I showed you in the picture. So it's got some nice spiral arms to it. We live close to one of them. But there are much bigger galaxies, really giants. The ones that I showed you that make the big bendy bits, those are giant galaxies. They can be up to 1,000 times larger. And we also have teeny tiny galaxies. For instance, the Milky Way has a few little companions that travel with it. If you've ever been in the southern hemisphere, like in Australia, you can actually see them in the night sky. They're called the Magellanic Clouds. Those are tinier galaxies. So we're pretty average, mid-size.
Amazing. Another great question about galaxies, and one that's making me think, do we know or are there planets in any of the other galaxies?
Yes, so this is something that keeps us quite busy thinking about, right? So we have billions of galaxies out there in the universe. Euclid is going to take pictures and measure the shapes of them. And each galaxy, as I told you, has typically another billion or so stars in them. And we know that most of the stars actually have a planetary system with them. So they have planets circling about them. So yes, there are lots and lots of other planets out there, also in other galaxies, for sure. We can't see them directly, but we can say these other galaxies look pretty similar to our Milky Way, and the Milky Way has lots of other planets. We know that, we can measure them, at least nearby. So yes, there will be loads and loads of them. And of course, the exciting question is, does any of those other planets have life on them? We don't know.
Yes, we've had that question lots and lots of times. So that's not something that we have discovered yet, is that right?
That's right, yes. So we don't know. The problem again is these things are awfully far away. And so it's too far away to see a planet, right? It's also too far away to even see an individual star like the sun. So we can't observe it directly. And also it's so far away if there was a little green man living in the Andromeda galaxy who decided, let's send the Earthlings a message, and they did that straight away, it would take hundreds of millions of years for that light to get to us, right? And so it's not exactly a direct communication that you can establish there, right? So it's very difficult to find out, but at least in our immediate neighborhood, so in our own galaxy and close to where the sun is, we know there are other planets. We call them exoplanets, and there's a huge variety of them. And there will be new space missions, one of them here being built at University College London, where I work as well. So I don't do that, but my colleagues are very excited about this. They're going to have another space telescope in maybe 6-7 years' time. That is going to look at some of these planets, take very exact pictures and try to find out what kind of chemistry, what kind of materials are on that planet. And then they might find out that there's, for instance, water on there, which we think is super important to have life. There might also be things like methane, which is sort of smells like foul eggs. It's very ugh, but it's a sign that there's life on that planet. And so maybe within the next 10 years, before you guys are grown-ups, we might have found a planet where there's definitely life on. Might not be little green men, it might just be smelly bacteria, but still, it could be life.
Amazing. So that's a very exciting thing to think about and maybe imagine about. And I'm sure lots of the students joining us will be using their imagination and thinking about what that might be like. We also have lots of questions about shooting stars. So why do we see them, and how fast do they move, and why do they move like that?
Okay, so shooting stars are actually not stars at all. What they actually are is much less exciting. They're little grains of dust, and they're very, very close, again, by astronomer standards to us. So in our solar system, we have lots of dust, small sort of crumbles, little bits of dirt floating about. For instance, they're left behind by comets in their trail. And then when the Earth passes through it, they start to fall towards Earth, and they get very hot, just like the sticker on Euclid got very hot as it got up through the atmosphere. If the little grains of dust fall down through the atmosphere, they also get very hot, and then they just burn up into a bit of flame. And that's what we call a shooting star. So it's just a little piece of dirt that burns up in our atmosphere.
Fantastic. Who knew? That's a really interesting and fun fact that maybe we can share with our families or our friends when we're talking about the talk later on. Another great question about galaxies, and how come we can see different colours in the galaxies?
Ooh, that is a very good question indeed. Actually, it's something that keeps us busy in our research as well, to understand the colours of galaxies. So what you see in a nice swirly galaxy, like the big picture I showed you, you see lots of blue and sometimes even pink as in that galaxy. And those are stars that are relatively young. Young, again, with astronomers, you always have to be a bit careful what they mean. Young means they're just a few million years old. We call that young. So they formed fairly recently. And so they're often very bright and very energetic, sometimes a bit violent. They explode. They tend to go off in a supernova quite quickly. And you find them a lot in the spiral arms. And so that's why you see blue in those galaxies. Then we've got old galaxies, old meaning a few billion years old, almost as old as the whole universe is. And those tend to be yellow-orange in that color. And that's because they are made up of old stars. Those send out most of the light. And those stars are very, very big and red and old, and they're about to die, sometimes in a sort of slow, boring death where they just fizzle out. Sometimes even those go off in a big supernova. And so that gives us more sort of a yellow-orange glow. And understanding how exactly that works and how many galaxies tend to be more in the old orange camp, in the lively blue camp, that's something that we're still trying to work out.
Fantastic. We also have lots of questions about your job specifically, Benjamin. So why did you become a professor of astrophysics, and what were you interested when you were in school? What subjects did you like, and what were your hobbies?
Right. Okay, so how this all started is when I was a young lad, maybe a few years older than you will be, I got a little telescope as a present. I don't even know why, whether I asked for it or not. At least I got one. And no one in the family knew how actually to operate a telescope. And so I had to sit down, get some books from the library and work out how do you actually observe the sky with a telescope. And so that took me a while, and then I worked that out. And then I could see things, but I didn't understand what I was seeing there, right? You just see lots of bright or faint spots there. And so then I started reading books about physics and astrophysics that tell me exactly how does a star work, what is a star, and then the fuzzy bits, there can be nebulae or there can be galaxies, and then I needed to learn about that. So something like you had the head start, you know already what galaxies look like. I had to read books about this and work this out. And so that slowly drove me towards, maybe astrophysics, astronomy, that's really interesting. And so then I picked this up at university and became an astrophysicist.
Fantastic. Would you believe that in that amount of time, we now have over 300 questions? So I don't think we're going to have time for all of those questions. But as I said, I'll be sending on all of your questions to Benjamin afterwards. Thank you all so much for the amazing questions that you have included. But we've run out of time, I'm afraid. So I would just like to thank all of your schools and all of your teachers for joining us and all the students who are with us, but especially to thank Benjamin for this fantastic inspirational talk. I'm sure there's lots of rounds of applauses in classrooms right now. I hope everyone has a great rest of the day. Thank you for joining us. And Benjamin, thank you so much.
My pleasure. Great to talk to you. Bye-bye.
Bye, everybody.